Let us solve physical metallurgy questions. The Miller indices of the direction common to the planes 111 and 110 in a cubic system is. So guys, whenever this type of question is asked, then you need to solve using the concept. Like suppose you have the two planes, right? Okay. This is your first plane, which is 111. This is your second plane, 110. And there will be a line which is the common line. Okay, so we need to find the Miller indices of this. So whatever be the Miller indices of a plane, so that is acts as a norm, right? So 110 is also norm. So from this line also, if you try to show this normal, then the angle between this n, that is the normal of 111, and the line will be 90 degree. Similarly, the angle between the normal of this 110 plane will be 90 degree to this line. So when we have 90 degree, that means the cross product will be 0. Right? So let the Miller indices of the line be A, B, C. Right? That means so 111 dot this A, B, C should be equal to 0. Next 110 dot A, B, C should be equal to 0. So here it will be A plus B plus C is equal to 0. Next it will be A plus B plus 0 is equal to 0. That we can write it 0C. Next, how do you find the ratio of this? We take first A, right, and multiply here and here. So it will be 1 into 0 minus 1 into 1 is equal to B. Now we have taken this B. Then in the clockwise fashion we will move. So we multiply this C part. So 1 into 1, right, minus 1 into 0. Now let us take this C1. So we will multiply this, right. So 1 into 1 minus 1 into 1. So A by minus 1 is equal to B by 1, which is equal to C by 0. So the ratio will be like 1 bar 1 0, right. So the correct answer will be 1 bar 1 0. Fine. So this is one method. Other method is you can directly choose from the option and do the dot product with this, right, and you can find where it's satisfied, right. So you will see this is the option C is satisfied. If you take this option D, so here it will be remaining like 1. If you do dot product of this 1 bar 1 1 to 1 1 1, you left with 1. So this is not right. Next question. The energy dispersive spectrometer, that is EDS, in an electron microscope does chemical analysis by analyzing the energy of. Okay, so you know, in the case of ECM, suppose this is your sample, then we pass high energy electron beam, right. So when we pass this electron beam, okay, so there are some electrons which are scattered, right. So this is called as back scattered. Okay, some back scattered electrons are there. Then we also have some secondary electrons. Secondary electrons generated from the samples, right. So when these electrons are generated, then what happens to fill the position of the valence, the electron from the outer shell come to the lower shells, right. So that produces wave, that is basically X-rays, that is produced in that range. So using by measuring the energy of that, okay, So it produces wave, and this is like X-ray. So by measuring the energy of this, we do the chemical analysis. So basically the X-ray. By using the secondary electrons, we generate the image. Then backscatter electron, so we see the image. Our electron has some other characteristics, but not this. Right? Next, in heterogeneous nucleation, the radius of the critical nucleus does not depend on. Okay, so this is very good question. See, this is talking for a heterogeneous. So we have homogeneous and heterogeneous. So one thing that should be clear, that the critical size of radius in homogeneous and heterogeneous remains same. So R star equal to minus 2 gamma S by delta GV. So here also we have the same expression. Okay, so R star. So this R star does not depend on. Okay, let's see. Contact angle. So is there any term related to contact angle? Is there any theta? So no. So I think it should not depend on contact angle, right? So but let us see other options also, like undercooling. Undercooling means what is the amount of undercooling from the melting point to the temperature. So that term takes from here. Delta GV we can write as delta H, right? Delta H T minus G by T, right? Can write like this also. Fine, everyone. Or we can write it like Tm minus T. Okay, because the delta H G is equal to delta H minus T delta H. So delta H minus T delta H by Tm. So delta H Tm minus T and Tm over here. So this R star depends on this undercooling, right? Here also same thing. So it depends. So here should not be the answer. The surface energy of the interface between the product and the parent phase. So surface energy, that is gamma. So it depends. This should not also be the answer. Enthalpy change per unit volume of the potential. So here the term delta H is there. Okay. So the only thing on which it does not depend is the contact angle. Next, the third peak in the X-ray. Here it will be X-ray diffraction pattern of a polycrystalline BCC. So in the case of BCC, what is the H square plus K square plus M square value goes like? It goes like 2, 4, 6, 8, 10, or even more. So third, it will be 6. So using which we can get this 6 value. So suppose here I do H square plus K square plus 1, so it will be 3. Here it will be 2. Here it will be 6. And here it will be 8. So the 6 will be the correct one. Option C. Okay. Next, number of slip systems in an ideal closed packed hexagonal structure. Hexagonal it is, right? So hexagonal, we have the structure like this. Okay. So this is your slip plane in the hexagon. And what are the slip direction? One is, second is, sorry, first this, second this, and third this. First, second, third. So there will be 3 slip system because direction, 3 direction, and 1 lane. Right? So 3 into 1 equal to 3. Next, driving force for grain growth after completion of recrystallization. So here the recrystallization has happened, right? So what are the methods before recrystallization? We have the cold work, right? So from here you can understand we have the cold work material. Then we do the heating. What is the first step in this? It is the recovery, right? Recovery. Then second is the recrystallization, where we have some aqueous rings, right? Now after this, what will the energy that will drive the growth of the grains, right? So see, stored energy of cold work, no. Because the stored energy of this cold work has helped you in this recovery and the recrystallization. Okay, so this is no. Vacancy concentration. No. Is it the vacancy concentration which is allowing the grain growth? No. Dislocation density in the crystal? No. Dislocation density which is present, it is the it is the driving force for this recovery method, because decrease of dislocations takes place during recovery. What is the left one? That is the grain boundary curvature. Yes, the grain boundary curvature. Because during the grain growth, we want that the grain should be higher. Right? Grain size increases. So let's suppose these are the grain. So after this grain growth, it should become like this. So the grain boundary area decreases. So that basically decreases overall the energy and it makes it more stable. Okay. Next, which of the following are not commercially manufactured by powder metallurgy? So what are the things which are not commercially manufactured? See, like it can be manufactured, but is it commercially manufactured? No. See, aircraft brake pads. So this aircraft brake pads are always made by this powder metallurgy and it is commercially made. Okay. So this will not be the correct answer. Self-lubricating pad. This is also very well made by powder metallurgy. Tungsten carbide. Yes, this tungsten carbide tools are also very much made by this powder metallurgy because of this high melting point. Right? So now next thing is turbine blades. So turbine blades are made by basically casting. And this is casting so that we want to produce a single crystal. Right? Using other method, that is directional solidification. Next. The question is the theoretical density of an FCC metal with atomic radius and atomic weight of 0.144 nanometer and 197 gram per mole respectively is approximately okay. So we have FCC metal and we need to find the density of this. To find the density we need mass and the volume. In the case of unit cell, the formula is like number of atoms into the mass of each atoms divided by this Avogadro number and the volume, that is the AQ. Fine. So I think everything is known. N value is here 4, M is given, then Na we know and A also we know. So just put the values. So rho is equal to N is how much? 4. Mass is 197 gram per mole, right? Gram per mole. And 1 mole contains 6.023 into 10 power 23 atoms, right? So fine here. Then A cube, that is the volume. So here we have the atomic radius. So in the case of FCC, we know the relation, that is 4r is equal to root under 2a. So a will be equal to 2 root 2 r. So a we can write 2 into root 2 into r, that is 0.144, right? So how much it will be? You can do the calculation. So it will be around 0.407. Okay, and this will mean nanometer, right? So we can put here 0.407 to 10 power minus 9, so it will be in meter, right? Okay, so the density from here, it will come in the unit of gram per meter cube, right? So next task will be to convert it into kg per meter cube. So you need to take care here. So do the calculation first. 4 into 197, 6.023 to 10 power 23 into 0.4 to 10 power minus 9 the power 3. So it is like 20442470. Let me check the calculation. Sorry, there is some correction. It is basically 194,05736.35 gram per meter cube. So now if we convert it into kg, so it will be divided by 1000. So it will be 19405.736 kg per meter cube. Okay, so which one is the closest answer? So it is the option C. Alright guys, so it matches with option C. Okay, next. A recrystallization process is 20% complete after 45 seconds and 85% complete after 75 seconds. Okay, assuming Avrami kinetics, the value of Avrami exponent n is. Okay, so roughly the recrystallization follows curve something like this, right? So it shows fraction of completion versus time, and the equation is x equal to 1 minus e to the power minus k to the power n, right? So this is our x is the fraction completed. Okay, fraction completed. Okay, so in the first of the case it is 20% complete. So what is the fraction it is complete? So it is like 0.2, right? Next it is 85, that means 0.85. And what is the time for this? Time is okay, and what is the time for this? It is 45 second. Next it is 75 seconds. So we put these values and we need to find this n value, right? So we have here three unknowns like n, k, okay, and this time we know, okay, fine, we have two unknowns like n and k. X value we will get from the question. So let us see how we can find it. We need to eliminate this k, right? So we need to think in that direction. So it will be 0.2 is equal to 1 minus k t here in the first case it is 45 to the power n, right? So we can write it as 0.8 equal to e to the power minus k 45 to the power n. If suppose I take ln on both sides, ln 0.8 is equal to minus k 45 to the power n. We can write like this. So first equation we have. For the second case we can write 0.85 is equal to 1 minus e to the power minus k time here 75 to the power n. So similarly, so it will be 0.15 is equal to e to the power minus k 75 to the power n. So take the ln equal to minus k 75 to the power n, right? So we have these two equations. Now suppose we want to eliminate this k, so we can directly divide these two equations, right? Or from first equation we take the value of k and put it in the second case. So you can do anything. So I am just dividing it. Okay guys. So now suppose first divided by second, then ln, sorry for this, ln 0.8 is equal to minus k 45 to the power n, it will be ln 0.15, okay, 0.15 is equal to minus k 75 to the power n. So k will be cancelled. So you need to take the help of calculator. Ln 0.8 divided by ln 0.15. Find this. So it will be 0.1176 is equal to 45 by 75 is how much? It is 0.6. So it will be 0.6 to the power n. So next we need to take ln again. So ln 0.1176 is equal to n ln 0.6. So n is equal to ln 0.1176 divided by ln 0.6. So n I am getting 4.19, okay, and this is the correct answer. So n is equal to 4.19, okay. Okay guys, now let us proceed for the next question. Silicon is doped with arsenic, okay, it is doped with arsenic, and the concentration of this arsenic doping is 10 to the power 20 atoms per meter cube. Suppose we have 1 meter cube of the sample, then we have 10 to the power 20 atoms of this. At room temperature, the electron and hole mobilities in silicon. So the mobility of electron and the hole are given respectively. The conductivity in ohm meter inverse at room temperature for silicon doped with arsenic is, okay. So see, we have the arsenic, right? So what is the atomic number of arsenic? Mobile? The atomic number of arsenic is 33, and if you see in the periodic table, so it is in the group 15, right, just next to the group where the silicon sits. So this silicon is present in group 14, and this arsenic is present in group 15. Okay, and this silicon has 4 valence electron, arsenic has 5 valence electron. So whenever a pentavalent atom is added in the silicon, then we get one extra electron, right? We get one extra electron, fine. And whenever a trivalent is added, like boron, gallium, then we get one plus, that is called as the hole or the lack of electron, right? Suppose we add group 13 element, we will get plus, group 15 element will get minus. Okay, so for one atom of this arsenic we are getting one electron, right? Okay, so in this case we will have only the electrons, right, because the addition of this arsenic is given and nothing more information is given whether the silicon itself contains some holes or not. Okay, so since no information there, we can take it as 0, right? So we have the concentration 10 to the power 20. So the concentration of electron will be 10 power 20 per meter cube, and for the hole it will be 0, right, per meter cube. So we know this conductivity formula, that is defined as, that is concentration into this mobility into the charge of an electron. Okay, and concentration of electron in the first case we can again write it like concentration of hole, that is plus mobility of hole, here it will be electron, then the charge, right? Since here it is 0, so we need to neglect this one, so we will come to here. So concentration of electron, it is 10 power 20 per meter cube. What is the mobility of hole? So it is 0.14 meter square per volt second. What is the charge? 1.6 into 10 power minus 19 coulomb, right? Okay, so what is the conductivity? Okay, so it will come in the standard unit by itself because all are written in the standard unit, right? So now do the calculation. 10 power 20 into 0.14 into 1.6 to 10 power minus 19. Okay, so I'm getting 2.24. okay, so this is 2.24 and the unit will be omega m inverse. Okay, so by itself it is in the standard unit because this volt, second and coulomb are in standard. Okay, everyone, I hope you are able to understand this, right? Next, 4 eutectoid steel samples. So we have 4 eutectoid, right? tight sample, that means it contains 0.8 weight% carbon. In some books it is given like 0.77, 0.78, so all are correct. Okay, it depends what you choose, but it's correct. Samples like W, X, Y and Z. Okay, and these all samples are austenites. Okay, austenized, okay, and then subjected to normalizing, quenching, Mar tempering, okay, and it will comma, Mar tempering, normalizing, quenching, Mar tempering and Osh tempering treatments respectively. Which of the following statements is not correct? Okay, so the four samples, so 1, 2, 3, 4. First, sorry, let me write like this: 1, 2, 3, 4. So 1, it is going under normalizing. Next, it is going under quenching, then Mar tempering, then Osh tempering. Okay, so the it talks about the microstructure in the options. So what happens after the normalizing? We'll get the perlite because slow cooling. Quenching, we'll get this martensite. Okay, and in the case of Mar tempering, also we get martensite. But the martensite is such that we avoid quench cracks, means there are no chances of cracks formation in the Mar tempering process. Then last is Osh tempering. So in the case of Osh tempering, we get this bainite, right? If you want to understand through this CCT diagram or TTT diagram, so see here, the first it is like this, right? So it is your normalizing. Next it is the quenching. So quenching is just like this, quenching. But when you go to this Mar tempering, so we have like MS over here, there's MF. So we'll go like this, but just above this MS we will hold, so that the temperature, suppose this is the sample, it has got some thickness, so that the temperature of this center is equal to temperature of this external. So we give the chance for the equilibration, because the temperature decrease will be faster in the case of this surface than the bulk, right? So that we allow the chance to equilibrate, then we do this cooling. Okay, in the case of this Mar tempering. Next is Osh tempering. So in the case of Osh tempering, we cool it rapidly up to here and we allow to transform to bainite. Okay, fine. So the first option, the microstructure of the sample W will be fully perlite. W is going under, so it is W which is going under normalizing, then X, then Y, then Z, right? So it is correct. The microstructure of sample X under quenching, so it will be martensitic. Yes. The microstructure of sample Y will be untempered martensite. Okay, sorry, I have written the wrong statement in the option. If you see the question, so it is basically talking of tempered martensite. Okay, the microstructure sample Y will be tempered martensite. So basically it will be not tempered, means normal martensite. So this is the incorrect statement. The microstructure of sample Z will be bainite. Yes, it will be bainite. So the option which is not correct here, it will be option C, right? Next, assertion and reason type question. Hardenability of steel can be increased by adding certain alloying elements. So yes, this is correct. When we add certain alloying elements like moly, chromium, nickel, so these increases the hardenability. The alloying elements can provide a fine dispersion of alloy carbides. Yes, when we add this moly, it forms moly carbides. Chromium also has the tendency to form chromium carbide. Like niobium, we add the niobium carbides. These are formed. Okay. But is it the reason to increase the hardenability? No. The carbides, these things which are formed, these are actually acts as nucleating sites for some other phases, like during the transformation it can form ferrite, but so that's why it is not significant. So the reason R, basically the R statement is correct, but it is not exactly the reason for that, the hardenability. Okay, so what is the reason of this hardenability increase? Okay, when we add the alloying element, because basically it helps in substitution of solid solution, and this this allows the martensite to be formed easily. Okay, let's see, both A and R are true, but R is not a correct reason for A. So this is the correct option. Both A and R false. No, A is true, but R is false. No, both A are true and R is true. Okay, next. Consider the following collection of polymer chains. Okay, number of molecule. So here it is given number of molecule 10, 5, 4, 2, 1. Okay, molecular weight is also given. Fine. So guys, for this, let us find first the number average molecular mass. So that is sigma NIMI, right? So 10 into 2800 plus 5 into 3000 plus 4 into 1200 plus 2 into 3600 plus 1 into 1000 divided by this 22. So it comes to 545.4. And we have this ethylene monomer, right? So when we have this ethylene monomer, so it will be C2H4. So it will be 12 into 2 plus 4, so it will be 28. So this dp, degree of polymerization, will be 2545.45 divided by this 28, right? 2545.45 divided by 28. So it will be 90.90, which is close to 90.91. That is the option P, right? Let us proceed for next question. At 910 degrees centigrade, gamma iron transformed to iron, resulting in a percentage volume expansion. Okay, so it transforms from FCC to this alpha iron, which is the BCC, right? Which is the BCC. So from this FCC we are getting to BCC. Is there any expansion of volume? So yes. So this is what it happens during martensitic transformation also. The volume actually increases. Okay, so let us see here what is the volume increase. Okay, so for this, right, see here, I will draw the crystal structure of both FCC and BCC, right? We have body center here, and the FCC we have the face center. Okay, now tell me, what is the thing which does not change while getting transformation from FCC to BCC? We have the iron atom here, and similarly here also it will be iron atom, right? So iron atom is made of this proton and the electrons, right? So the size of this iron atom will never change, right? So this size of atom is equal to constant. So size is constant, that means radius is constant. So what will be the change in the A value? A in the case of FCC and A in the case of BCC will be different. The edge length will be different, right? Now see, we need to find this volume expansion or contraction. So here it is given that expansion takes place. So let us see. So the volume of this FCC will be AFCC cube divided by this 4. Why 4? Because we want to calculate the volume per unit atom, right? Because the number of atoms, yeah, one more thing, number of atoms will be also fixed, right? And we know whenever we have this FCC, so we have effectively 4 atoms. In the case of BCC, effectively we have 2 atoms, right? So we need to take the average volume, right? So volume per unit atom, right? So we are taking the volume of FCC and it has got 4 atoms. So volume divided by number of atoms. So in the case of BCC, so it will be A BCC cube by 2 atoms, right? So in the case of FCC, we know 4R is equal to root 2A. So A we can take 4R by root 2. In the case of BCC, A we can take 4R by root 3. So just put this. So 4R by root 2 cube by 4. Here 4R by root 3 cube by 2, right? We need to find the percentage of the volume change, right? So volume of this FCC, right, and minus volume of this BCC divided by volume of this FCC, okay, 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 into 100. So it will tell you in the percentage. So what is the basically the volume expansion? If the value will be negative, that means expansion happens. So volume of this FCC, it is 4R by root 3 cube by 4 minus 4R by root 3 cube by 2 divided by 4R by root 3 cube by 4. What is the common thing here? One thing is common, that is 4R. So can we just cut it? Yes. Next, what we can write? Okay, so 1 divided by 4 root 3 cube. So we can write 3 root 3 into 4 minus here, see. Sorry, it will be root 2 over here, right? So you need to take precaution while doing the calculation. 1 3 root 3 into 2, 1 divided by 2 root 2 into 4. Now do the calculation. Okay, 1 divided by 2 Yes. So I got it as minus 8.86 percentage. So that means expansion of 8.8 percentage we are getting, we can say. So option D, right? Let us move. Next. In the above hypothetical phase diagram, the melting point of each pure component is 1000. So melting point of each component is 1000 Kelvin, and the eutectic temperature is 800 Kelvin. Eutectic is this one. The eutectic is located at the equiatomic composition. So it is very simple, I think. The equiatomic, that means this Nb is equal to 0.5. Okay, so it is given a mole fraction. The maximum solid solubility in phase is given by mole fraction Nb is equal to 0.1. So this is first case. The freezing range in Kelvin of the alloy with composition Nb is equal to 0.1. So what is the freezing range? So freezing range is over here, right? So see, this is very symmetrical phase diagram, right? So we can take this triangle and try to understand what is happening over here. See, this is the temperature difference here, right? This is the temperature difference over here, point A, B, C, D, E, right? So if I take it out, so A, B, C, D, E. So A is 1000 over here and B is 800. So what is the length of this? It is 200, right? Okay, and this line and this line, this CD will be parallel. So when we have a parallel line in a simple line, then it divides in the ratio, right? And how it divides? It divides such that, see, we can write AB by this, you know, AB by this CD is equal to, in this direction we can go like BE by this DE, right? By the properties of similar triangle, right? So this AB, this complete line of triangle ABE will be divided by this CD will be equal to this B, the total line of this triangle ABE to this next triangle CDE, that is DE, right? So this CD is equal to 200 into 0.4 by 0.5. So 40, so it will be 160, right? So 160 is the temperature difference. So here, yes. So 160 is the answer, the first one, right, everyone? Next, let us see. I have solved in the second part, so sorry for that. On cooling an alloy of composition Nb is equal to 0.2. So let us take any alloy Nb 0.2. Okay. The fraction of pro-eutectic alpha phase. Pro-eutectic means before the eutectic line, right? At the eutectic temperature is, so 0.2. So before eutectic, right? So we'll take the position just above this line. So the tie line will be our DE, right? And for this 0.2, let us take here like O. Okay, so we need to find this percentage alpha. So it will be alpha here, liquid here. So it will be OE divided by DE into 100. So O is how much? 0.5 minus 0.2. DE is 0.4 into 100. So it will be 3 by 4 into 100. So it will be basically 75%, or in the fraction it will be 0.75, right? So option A will be the correct one. Next question is, the diffusion couple shown above is made from two AB alloys, right? A and B, right? The initial composition of the two alloys is indicated in the diagram. The center line is at x equal to 0. The couple is held at an elevated temperature for 40 hours. Okay, 40 hours. Diffusivity D is equal to 3 into 10 power minus 11 meter square per second. Assume the diffusion couple to be infinitely long. Which of the parameters give the composition profile in the following form, right? So guys, for this type of situation where we have the two alloys with different concentration joined together, okay, like this and like this. So this is the junction. So at this junction, the initial concentration, we take it as the average of this, okay. So it will be basically 0.4 plus 0.5 by 2, that will be 0.45, right? So if you draw the concentration curve, so how it should be like something like this, okay. So from here, in the right hand side the concentration should increase, and in the left hand side the concentration should decrease, okay. And the x position is marked in the right hand side, right? So for that purpose the equation has been said like Cxt, that is for particular x with time t, equal to C1 plus C2 error function x by 2 root t. So C1 is some constant, C2 is another constant. So for this type of thing, C1 is always the average of this. So here it will be 0.4 plus 0.5 by 2, that is 0.45. And C2, okay, because it is in the x direction only and it is towards the material which has the higher concentration. So this C2 will be a positive value, right? And it should be the positive value such that it should be from the higher concentration 0.5 we will subtract the lower concentration, that is 0.4 divided by 2. So it will be 0.05. Okay guys, so it will be like this. Okay, people may confuse because in the book if you see, so they have given something like this, where we have this C1 and this C2. C1 has been taken as the higher concentration, right? And this Cxt, it is written as A minus B error function x by 2 root t. Okay, so here x is in the direction, so here the concentration is changing, so we have this minus sign to take care of that. But in this question the concentration was increasing, that's why we had this plus sign over here. Okay, so A and B, so in this case A is equal to C1 plus C2 by 2, and B here it will be C1 minus C2 by 2, right? The higher minus lower, that is C2 the lower concentration, divided by 2. So similarly C2 here we have done the same thing, 0.5 minus 0.4 by 2, that is 0.05. and since plus sign is already given here, so that thing has been taken care, right? So the correct option will be option A. Now next question. The composition at a distance x equal to 2 mm is approximately. So at 2 mm we need to find. So we have the equation. So we shall solve over here. So C at 2 mm at time 40 hours, right, is equal to C1, it is 0.45 plus 0.05 and error function of x divided by. So here it has told us to assume that error function of x equal to x for small x, means if the value of this is very small, then we can take it directly equal to the value itself. So we are taking it directly because it is already given. Okay, so x is 2m, so we need to convert into SI unit, then 2 root over dt. T is 3 into 10 power minus 11 into time. Time is 40 hours, so 40 into 60 into 60. 40 hours into first 60 will give you the minutes, and the second 60 will give you the seconds, right? So now do the calculation. So here I am getting C is equal to 0.474. Okay, so I think this is the correct answer. Okay guys, so hope this will help you for your preparation. In case of doubts, please contact me. Thanks all.